This is a cylindrical rotor generator, the type used in modern steam and gas turbine power plants around the world. Designed to operate at extremely high rotational speeds, its rotor must withstand enormous mechanical forces throughout decades of operation. Once the generator's output, operating speed and electrical characteristics have been finalized in the digital design stage, manufacturing can begin. The process starts with a single massive steel forging, which will eventually become the heart of the generator. Working in close coordination, the operators of a hydraulic forging manipulator and a 10,000-ton forging press repeatedly compress, rotate, and reform the glowing steel. Hour after hour, the glowing forging gradually takes on the cylindrical profile of the future rotor shaft. Long slots are machined along the rotor body to accommodate the field windings. Unlike the large salient-pole rotors found in hydroelectric generators, this design uses a long cylindrical body with only 2 poles. Its streamlined geometry allows it to spin safely at 3,000 or 3,600 revolutions per minute while enduring enormous centrifugal forces. The machined slots are then filled with insulated copper conductors, carefully stacked layer by layer to form the rotor field windings. Each conductor must be electrically isolated, not only from the steel rotor body, but also from the neighboring turns surrounding it. Once in place, the windings are compressed and secured with tremendous force, preventing even the slightest movement under the enormous centrifugal loads generated at full speed. At the same time, the entire insulation system must continue to perform reliably while operating temperatures climb beyond 130 degrees Celsius under heavy electrical load. Supplying electrical current to a rotor spinning at thousands of revolutions per minute presents a unique engineering challenge. To solve this problem, the field winding terminals are connected to 2 slip rings mounted directly on the shaft. Multiple carbon brushes maintain continuous electrical contact with these rotating rings, allowing direct current to flow into the rotor while it remains in motion. Using several brushes in parallel distributes the electrical load and ensures reliable operation under the extremely high excitation currents required by large turbine generators. Once energized, the rotor field winding is ready to establish the magnetic field at the heart of the machine. Massive retaining rings are then installed at both ends of the rotor, securing the field winding against the enormous centrifugal forces generated at full speed. Before being inserted into the stator, every rotor undergoes precision balancing tests. At 3,000 revolutions per minute, even the smallest imbalance can generate enormous forces and damaging vibrations. While the rotor provides the magnetic field, the stator is where electrical power is ultimately produced. Its core is built from electrical steel, specially engineered for magnetic applications, allowing magnetic flux to pass through efficiently while minimizing energy losses. Rather than using a single solid block of steel, the core is assembled from thousands of thin insulated laminations to suppress eddy currents that would otherwise generate heat and waste energy. Precision slots are stamped into each layer before assembly, creating the channels that will later house the stator windings. While the stator core provides the magnetic pathway, the copper windings are where electrical energy is ultimately produced. Rather than using a single massive copper conductor, generator windings are built from multiple insulated conductors arranged in layers. This allows them to carry enormous currents more efficiently while reducing heat, eddy current losses, and skin effects within the conductors themselves. The conductors are then carefully formed using dedicated tooling, allowing the copper to deform without damaging the insulation system or introducing microscopic cracks on the surface. Once formed, the coils receive additional layers of insulation before being compressed into winding assemblies precisely matched to the stator slots, ensuring complete electrical isolation from the grounded steel core surrounding them. The individual windings are then installed and interconnected to create 3 separate groups of coils, forming the generator's 3 electrical phases. This remarkably simple arrangement forms the foundation of the 3-phase power system used throughout modern industry and electrical grids around the world. As the rotor spins, its magnetic field passes through the stator core and cuts across the stator windings. This changing magnetic field induces voltage in the conductors. One remarkable aspect of large synchronous generators is that while their electrical output may constantly rise and fall with demand, the rotational speed of the rotor must remain almost perfectly constant. Even a small change in speed would immediately alter the frequency of the electricity being produced. For this reason, power systems around the world are designed to operate at a tightly controlled frequency of either 50 or 60 hertz. So, if the rotor speed cannot change, how does a generator produce more power? The answer lies in the strength of its magnetic field. By increasing the direct current flowing into the rotor windings, the generator produces a stronger magnetic field. As more electrical current flows through the stator windings, they create their own magnetic field that pushes back against the rotor's motion. This electromagnetic resistance attempts to slow the machine down. To keep the rotor spinning at exactly the same speed, the turbine must deliver additional mechanical power to the shaft. More electrical power out therefore requires more mechanical power in, while rotational speed remains unchanged. But not every generator has the luxury of spinning at 3,000 revolutions per minute. Many industrial generators operate at much lower speeds, requiring a different rotor design altogether. Instead of hiding the magnetic poles inside a solid steel body, the field windings are mounted directly onto individual poles distributed around the rotor itself. Each pole carries its own excitation winding, creating alternating north and south magnetic poles around the circumference of the machine. By increasing the number of poles, the generator can continue producing the same 50 or 60 hertz electricity, even while rotating at much lower speeds. This is the defining architecture of the Salient-Pole Generator, the design most commonly found in hydroelectric power stations around the world. Instead of a single forged rotor body, each magnetic pole is manufactured as an individual assembly, complete with its own field winding and insulation system. The poles are then installed one by one around the rotor body to create the final machine geometry. This modular construction makes it possible to build generators far larger than would ever be practical with a single-piece rotor. In some of the world's largest hydroelectric power stations, these generators can carry as many as 16 pairs of magnetic poles around a rotor more than 10 meters in diameter and weighing over 200 tons. Only the immense potential energy stored in millions of tons of water high above the turbine is capable of driving a machine of this scale, rotating the rotor at speeds of just over 225 revolutions per minute. More poles mean more magnetic field cycles are produced during each revolution. As a result, the rotor can spin much more slowly while still maintaining the same electrical frequency of 50 or 60 hertz. Despite its very different appearance, the operating principle remains exactly the same as in a high-speed turbine generator. As the rotor turns, Each passing magnetic pole causes the magnetic field inside the stator to rise and fall continuously, inducing electrical energy in the stator windings. Electrical output is still controlled by adjusting the direct current supplied to the rotor field windings, strengthening or weakening the magnetic field as required. As electrical demand increases, the stator produces a stronger opposing electromagnetic force that attempts to slow the rotor down. To maintain a constant rotational speed, the turbine control system responds by opening the guide vanes, allowing more water to flow through the turbine and increasing the mechanical power delivered to the shaft. The result is a generator capable of following changing electrical demand while maintaining a perfectly stable grid frequency. Over the past century, engineers experimented with many different electrical frequencies. Lower frequencies required larger motors, generators, and transformers, while higher frequencies increased electrical losses and made power transmission more difficult. In the end, 50 and 60 Hz emerged as the practical balance between machine size, efficiency, and long-distance power delivery. More than a century later, nearly every large generator on Earth still operates to that same invisible rhythm.